Okay, good. All
I
right. So,
can.
all right, good. So let me minimize that. Wait until this YouTube thing takes over. Okay, looks like my YouTube. Whoops. Let me turn down that volume or mute it. Okay. So let me go to where we left off the last time. So we were talking about previously the stoichiometric equivalents or mole fractions or conversion factors that we use when it comes to relating the moles of different substances involved in a chemical reaction. And of course, the key thing I would say that you need to remember is to make sure that the equation is balanced, because if the equation is not balanced, then you'll end up with more than likely the wrong mole fractions, and therefore the subsequent calculations will be incorrect. Okay, so with that out of the way, let me talk about this concept of limiting reactants. And again, this is something you should have met before. Basically, you can have situations where the amounts of reactants involved in a reaction to begin with are not molar equivalent. So that means that what will happen in those situations is that one of the reactants will be completely used up and the others would have some excess left over at the end of the reaction. So the reactant that is completely used up is called a limiting reactant, and the other reactants are called the excess reactants. Now, to illustrate this, we're going to use this example of somebody given the task of preparing a packaged meal based on the combinations that you see here. You have one sandwich, two cookies, and one orange, and when they come together, they form a meal, all right? So you may be given a situation where you're given 11 sandwiches, 16 cookies, and 10 oranges, all right? Obviously, this is not a 1:2 to 1 ratio as established by the formula used to determine the amount of the different items to make one packaged meal. So the question now becomes, how many meals can you get from this combination here? So if you take each item in turn, let's say you take the 11 sandwiches, right? Well, according to this formula here, 11 sandwiches will require 11 sandwiches will require 22 cookies, and we don't have 22 cookies here, we have 16, and will also require 11 oranges. We have 10 here, not 11. So therefore, we know that not all the sandwiches will be used up to make as many packaged meals as possible. If you look at things from the standpoint of the cookies, or let me just say the orange first, 10 oranges will require 10 sandwiches, which is fine because we have 11, but it will require 20 cookies. We don't have 20 cookies, we have 16 cookies. So we know that not all the oranges will be used up. Now, if we look at things from the standpoint of the cookies, we have 16 cookies, and based on the formula here, 16 cookies will require 8 sandwiches and 8 oranges, all right? And we have more than enough oranges and sandwiches for 8 of each of these to be used. So therefore, we know that all the cookies will be used up. We know that 8 of the oranges will be used up and 8 of the sandwiches will be used up, right? So therefore, in this context, the cookies would be the limiting item. And therefore, based on that fact, it is the cookies that determines how much product you will end up with. And in this particular case, you're going to end up with 8 packaged meals. Whoops, sorry about that. So basically, in this sense, the cookies are the limiting reactants, and this would be the amount of packaged meals you expect to get. And you're going to have 2 oranges left over. I'm sorry again, keep doing that. You're going to have 2 oranges left over, and you're going to have 3 sandwiches left over. And therefore, that would be the result of this situation. All right. So basically, the same idea can be applied to reactions. If you have one reactant which is limiting, then it will be used up. And if there are other reactants in that situation, there will be, some of it will be used up, but you're going to have some of those reactants left over. All right. So let's look at this situation. Let's say you're given 105 sandwiches, 202 cookies, and 107 oranges. Question is, how many meals can be made from these items, right? Well, if you start off with 105 sandwiches, the maximum number of meals based on the 1-to-1 ratio between the meal and the sandwich would be 105 meals. In the case of the cookies, the maximum number of meals possible would be 101 meals. And in the case of the oranges, the maximum number of meals would be 107 meals. So that's based on the calculations starting from each of the items that you're using to begin with. So based on the fact that the cookies will give you the lowest number of meals calculated, that means that the cookies will limit the amount of meals you'll get. In other words, the cookies will be the limiting reactant, which means that the sandwiches and the oranges will be in excess. So if you understand the concept behind what I just discussed, then you should be able to do problems of this type. So, and this is a typical limiting reactant problem. So the question says, magnesium nitride can be formed by the reaction of magnesium metal with nitrogen gas. So it starts off with that information. So the A part is asking how many grams of magnesium nitride can be made in the reaction from 35.00 grams of magnesium and 15.00 grams of nitrogen. All right, so you're given the reaction in words, right? And you're given the mass of magnesium and the mass of nitrogen that you're starting off with. And then the B section is asking how many grams of the excess reactant remain after the reaction. Okay, so the very first thing you need to start off with is a balanced equation. So the question gives you that the reactants are magnesium and nitrogen. And remember, nitrogen exists in nature as N2. The product of this reaction is magnesium nitride. So you have to figure out what the formula for magnesium nitride is. Well, magnesium is Mg2+, that's a magnesium ion. The nitride is N3 minus, which means that you're going to need 2 magnesium ions for every, I'm sorry, 3 magnesium ions, excuse me, for every 2 magnesium, I'm sorry, 2 nitride ions. So therefore, the formula for magnesium nitride will be Mg3N2. And of course, the next thing we need to do is balance this equation. And to balance this, in this case, we only need a 3 here. Okay, so that's the first thing. You have to have a balanced equation. If you don't have a balanced equation, then basically, as I said before, you run the risk of ending up with a wrong answer. Okay, now the question gave us 35.00 grams of magnesium. So what we need to do is find out how much product you expect to get based on this mass of magnesium. So the first step would be, we convert this to moles. 1 moles of magnesium above in this conversion factor, and down here you're gonna have the molar mass, which if I'm not mistaken, in fact, let me check here just to make sure. I think it's 24.31. Okay, where did I put that table? Okay, I guess I have to go to file.
Here, I can find it real quick.
Oh yes, please. That would help a whole lot. I think it's 24.31, but I'm not, I don't want to. Let me get the tables here in the meantime.
Where is it all?
Okay, seems like
I got it. Magnesium
Mg
is 24 mg. Yep, 24.31.
Well, hold on. Let me see here. Okay, I'll go with 24.31. Okay, so let me go back here. So down here, I'm going to put 24.31 grams of magnesium. All right, so what we have done so far is to calculate the moles of magnesium. So the next step is to go from moles of magnesium to the moles of the product, which is magnesium nitride. And this is the reason why the equation being balanced is very important, because now we have a coefficient of 3 for the magnesium and 1 for the magnesium nitride. So the mole ratio here is going to be 3 moles of magnesium and 1 mole of magnesium nitride. All right. And then we need to use our calculator to Work this out, 35.00 divided by 24.31 divided by 3. Okay, so according to my calculations, when rounded off to 4 sig figs, this is going to be equal to 0.4, I'm sorry, 0.4799 moles of magnesium nitride. So that's how that is done for the magnesium going to magnesium nitride. And we're going to do a similar thing for the nitrogen. The question says that you're given 15.0 grams of nitrogen. Calculate the moles like we did before. 1 mole of nitrogen. Whoops. I hate when this happens. Okay. 1 mole of nitrogen down here. And then the molar mass of nitrogen is 28 for one nitrogen atom is 14 point something, 14.01. So for 2 nitrogen atoms, it's going to be 28.02. So you're going to have 28.02 grams of nitrogen down here. And then we convert from moles of nitrogen to moles of magnesium nitride. In this case, it's a 1-to-1 ratio. So we're going to have 1 mole of nitrogen down here, 1 mole of Mg3N2 here. And again, do some number crunching. 15 divided by 28.02 times 1 gives you, okay, so according to my calculation, this works out to be equal to 0. Okay, what's going on here? 0.535 moles of Mg3N2. So therefore, we compare these two numbers here and here. This one is lower, which means that the magnesium in this case is the limiting reactant, all right? So to answer the question, because the question is asking for the mass of magnesium nitride you'd expect to get, we simply convert that to moles. So 0.4799 moles of Mg3N2 multiplied by 1 mole, 1 mole of Mg3N2 down here. And up here, we need a molar mass of magnesium nitride. Now, since I'm a lazy person, I'm going to cheat a bit. I'm going to go to my molecular mass calculator. So I think this is the one I'm going to use. And what I'm going to do, the way this works, is that you just put in your formula, press calculate, and it gives you the molar mass. So for magnesium, it's 100.93. So let me go here, and I'm going to write 100.93 grams of Mg3N2 and work that out. So 0.4799 times 100.93. So according to my calculations, the mass of the product would be 48. I need to round off to 4 sig figs. So 48.44 grams of Mg3N2. All right. So that's basically how the A part is done. Any questions?
No, I don't believe so.
Okay, so going back to the question, the B part. Oh, looking at the wrong thing, PowerPoint. The B part is asking how many grams of the excess reactant remained after the reaction. All right, now, let me go back to what I was writing on before. You should recognize that, as I mentioned before, This is the limiting reactant, the magnesium, which means that this would be the excess reactant, all right? What the question is asking for is how much of this is remaining after the end of the reaction. So basically, you're going to start off with 15.00 grams, and we need to calculate how much of that 15.00 grams of nitrogen will remain after. So we have to find out how much reacted. So how do we find out how much reacted? We find out how much reacted with the limiting reactant. In other words, we're going to start off with the 35.00 grams, of magnesium. I hope this can fit. Convert to moles like we did before. 1 mole of magnesium divided by the molar mass, which is 24.31 grams of magnesium. And then we look at the mole ratio between the magnesium and the nitrogen. And that's a 1:3 mole ratio. So you're going to have 1 mole of nitrogen above, 3 moles of magnesium below. And then we're going to convert this to grams of nitrogen. So we're going to have 1 mole of nitrogen down here and 28.02 grams of nitrogen above. And we calculate this. So get out my calculator again. 35 divided by 24.31 divided by 3 times 28.03. And according to my calculations, this works out to be equal to 13.45. So here I'm going to write down 13.45 grams of nitrogen. Now, please remember, nitrogen, this mass here is the mass of nitrogen that reacted, right? So to find the amount of nitrogen remaining, we're going to subtract this from the original amount of nitrogen, which is the 15.00 gram. So I'm going to squeeze that up here. So mass of N2 remaining will be equal to the 15.00 grams that you start off with. And you're going to subtract from that 13.45 grams. And let me see what my calculator says. So according to my calculation, this works out to be equal to 1.55 grams. So 1.55 grams of nitrogen will remain. So this would be the answer to the B part. All right. Okay, any questions about that particular part of this example? Any questions? Okay, if there are no questions, then we're going to move on. So the next thing we're going to talk about is the whole idea of reaction yields. And again, this is something that you should be familiar with from your previous experience. What we have been working on, for example, in the last example, when we calculated the amount of product based on the amounts of reactants that we started off with, what we were actually calculating is what is known as a theoretical yield. The theoretical yield is basically the amount of product you expect to get. Now in practice, because we don't live in a perfect world, in practice, when you do experiments and you isolate your product and you weigh, what you'll find is that the amount of product is less than what you expect to get on paper, all right? So this brings us to the difference between the theoretical yield, if the world was perfect, and you get the amount of product you expect to get, and the actual yield, which is the amount of product that you get from the experiment, all right? So the measure of how successful the experiment is can be expressed as what is known as the percent yield, right? Where you take the ratio of the actual yield to the theoretical yield times 100%, and that would be the percent yield. But before we get to that, let me just say that there are some reasons why the actual yield may not be equal to the theoretical yield. And sometimes it's due to human error, poor technique. And sometimes you can take all the precautions in the world, and yet you don't get the theoretical yield as the actual yield. Sometimes you have competing reactions. Sometimes you have situations where the product itself reacts to form other substances. So, there are many reasons why the actual yield and the theoretical yield are not equal. So as I was saying, the percent yield is equal to the actual divided by the theoretical times 100%, all right? And in practice, theoretical yields, or I should say percent yields, are pretty low. If you get a reaction and you perform it and you get a percent yield greater than 90%, you're doing exceptionally well, right? Because very rarely do you get reactions where the percent yield is above 90%. It's more typical that you'll get percent yields, especially when it comes to organic reactions, probably in the 70 to 60 or even lower, all right? So just to give you some numbers, to give you some ideas to what is actually occurring in practice when it comes to the percent yields of reactions, all right? Okay, so that's pretty much what I'm going to say for yields. Let me move on now to discussion of solutions, because solutions are important when it comes to stoichiometry as well, because a lot of reactions occur in solutions, especially aqueous solutions. So for us to have an appreciation and understanding of what solutions are, remember solutions are made up of two components. You have the solute and the solvent. The solute is basically the substance that's being dissolved. The solvent is the substance that is doing the dissolving. Typically, if you have a solid dissolved in a liquid, then the solid will be the solute and the liquid will be the solvent. If you have two liquids, one dissolved in another, then the solute would be the liquid in smaller proportions and the solvent would be the liquid in greater proportions, all right? Now, there are several ways of measuring what we call the concentration of a solution. The concentration is basically the amount of solute divided by the amount of solvent or amount of solution, depending on which way you're trying to measure your concentration for your solution. The way we're going to talk about this today is molarity. The molarity is one way of expressing the concentration. And the definition of molarity is given right here. Molarity is equal to moles of solute divided by the liter of solution, right? And basically, the units, as far as molarity is concerned, because you have moles over liter here, the units of molarity can be expressed as moles per liter, or you can simply use uppercase M, all right? So uppercase M, you should understand, is the same as moles per liter, all right? So just to give you some examples of concentration, here we have two solutions of sodium chloride. This one is a 0.1 M solution of sodium chloride, and this was made as a result of dissolving 0.05 moles of sodium chloride in 500 mils of, and this should be solution, not water, but solution. All right, I'm going to explain why shortly. So please make a note of that. This should be 500 mils of solution. All right, so that's your 0.1 M sodium chloride solution. Over here, we have our 5 molar sodium chloride solution, which is made by dissolving 5 moles of sodium chloride in 1 liter of, again, this should be solution, all right? So basically, the terms dilute and concentrated are relative terms, because basically, if you compare these two, the 0.1 M solution is more dilute than the 5 molar solution, or you can say the 5 molar solution is more concentrated than the 0.1 M solution. And basically, what this also means is that if you were to look at the particles in the concentrated solution would be on average closer to each other, while in the more dilute solution would be on average further away from each other. Okay, so that leads us now to some questions here. Let me do something over here so I can get myself set up. Let me click on this. Click on that. And, oh, this is the wrong thing. Let me do this. let me do this. And then let me do that. And then this. And then that. Sorry about this, folks. I've had some technical difficulty earlier, so. All right, so let me scroll down. Okay, so let me get out of this here and go to my writing pad here, and let me eliminate all of that. Okay, so the first question says, how would you prepare a 500 ml of a 0.250 M solution of sodium phosphate? All right, and this is something that is done routinely in labs all over. You want a solution of a particular concentration of a particular volume, and you have to actually determine how much of the solute that you're going to weigh in order to make up the solution. So you have to actually put pen to paper and do your calculation first before you actually do the actual preparing of the solution. So what you need to do is determine the mass of the solute. So how do you determine the mass of the solute? Well, we start off with the 500 mils of the solution, and then we convert that to liters. So 1 liter of the solution would be equal to 1,000 milliliters of the same solution. And then we convert that to moles. How do we do that? We multiply by the molarity, 0.250 moles of Na3PO4 divided by 1 liter of the solution. And then the final conversion factor is the molar mass. So you're gonna have 1 mole of Na3PO4, and the molar mass will be up here, which means that, again, being the lazy person I am, I'm going to go to my molar mass calculator. So the formula for sodium phosphate is Na3PO4. Calculate. Okay, so according to the molar mass calculator here, that would be equal to 163.94 grams. So that is going to be up here, 163.94 grams of sodium phosphate. And of course, we're going to need our calculator to do our number crunching. 500 divided by 1,000 times 0.250 times 163.94. And according to my calculations, I have to round this off to 3 sig figs, so this should be 20.5 grams, all right, of sodium phosphate. So this is the amount of sodium phosphate that we need to weigh. So we're not finished with answering this question, because the question did not just ask us to calculate the mass of the solute. The question is asking us, how would you prepare this solution, right? So you need to follow this calculation up with a statement. So I would write something like, weigh 20.5 grams of Na3PO4 and add water to make a final solution of 500 mils. And that would be the complete answer to that question, all right? So that's basically how you do a problem of this type. Any questions about this one? Any questions about this example? No questions? Okay, let's move on to the other question. The question says, in an experiment, 15.0 grams of sodium hydroxide completely neutralizes. I'm sorry, let me show you the question. In an experiment, 15.0 grams of sodium hydroxide completely neutralizes 125 mils of phosphoric acid. The A part is asking for you to write a balanced equation for the reaction. So we have to identify, of course, what the reactants are, which in this case would be the sodium hydroxide and the hydrochloric acid. And we talked about neutralization reaction already, so you should know by now that the products will be sodium chloride and water, all right? So that would be the balanced equation, and that would answer the A part. Now the B part, going back to the PowerPoint here, is asking what is the molarity of the phosphoric acid solution? Oh, my bad, phosphoric acid, not hydrochloric acid. So I need to make some corrections here. Sorry about that. This should be H3PO4. And this should be sodium phosphate. So let me erase that. Okay, so here you're gonna have H, okay, what's going on here? Okay, I don't know what's going on here.
Oh, I think you've still got your eraser on instead of a pen.
Yeah, thank you. Thank you. H3PO4. And based on the acid-base reaction, neutralization reaction, stuff that we learned earlier, you should figure out that the formula for the sodium phosphate would be Na3PO4. Okay, so that's the correct equation. So the next question is what's the molarity of the phosphoric acid? Now the question gave you 15.0 grams of sodium hydroxide, all right? So what we need to do first is convert that to moles. So 1 mole of sodium hydroxide above, and below we'll have the molar mass. So let me go back to my molar mass calculator, NaOH, and this gives you a molar mass of 40.00. So let me go back to the 40.00 grams of NaOH. And then what I should have done up here is balance the equation. To balance this, we need a 3 here and a 3 here. So the mole ratio between the sodium hydroxide and the phosphoric acid would be 3 moles of sodium hydroxide, 1 mole of phosphoric acid, right? And then, because of the cancellation of these units here, the only unit remaining would be moles of phosphoric acid. And the question is asking for the molarity. So what we need to do is divide the moles of phosphoric acid by the molarity, by the volume, I should say. And the volume is 125 mils. We need to convert that to liters, 1 liter over 1,000 mils. And that would give us the molarity of the phosphoric acid. So let me do this calculation here. 1.5 divided by 40, divided by 3, divided by 0.125. And the answer I got is 1.00, because I have to round this off to 3 sig figs, 1.00. And the units here would be moles per liter, or M, all right? And that is how you calculate the molarity of the phosphoric acid. Now, the next question is asking, what is the concentration of the phosphoric acid solution in grams per dm cube? So basically you have the concentration in moles per liter, and you need to find out, based on question C, the concentration expressed in grams per dm cube, all right? Well, if you start off with the 1.00 moles per liter, well, first let me deal with the dm cube, the liter to dm cube conversion. If you look in the tables, you'll see that 1 liter is equal to 1 dm cube, right? So that won't change anything numerical as far as that is concerned. The liter units will cancel out, and you'll be left with moles per dm cube. But to convert from moles to grams, again, we're going to need a molar mass. So down here, you're going to have 1 mole of the sodium phosphate, and up here, the molar mass of the sodium phosphate. So let me go to my calculator again. Na3PO4. Calculate 163.94. I think I did this already. So that goes up here. So you're gonna have 163.94 grams, and that will be equal to, when you round out to 3 sig figs, 164 grams per dm cube, because the mole unit's going to cancel out here and here. All right, so that would be the answer for the C part. And then the answer for the B part is actually quite simple, because basically 164, squeeze it in here, grams per dm cube. If you convert from grams to milligrams, you're going to need to put 1,000 milligrams down here, 1 gram above, and then the next conversion factor I'm going to continue down here would be 1 dm cube over 1,000 cm cube. And what makes this convenient is that the 1,000 here, and okay, I made a mistake. This should be the other way around. Let me make a correction here. So this should be 1,000, wait a minute. Okay, I'm sorry, folks. I made an earlier error. Let me erase this here. So let me backtrack and correct stuff. Okay, so as I was saying, you need to convert from grams to milligrams. So the way you do that here is that you're going to have 1,000 grams here. That's a mistake I made earlier. And 1 gram here, and 1,000 milligrams up here. And then the next conversion factor, you're going to have 1 dm cube above and 1,000 cm cube or milliliters below. That's the relationship between the dm cube unit and the milliliter unit. So what's going to be convenient here is that this 1,000 will cancel out this 1,000, and the grams will cancel out here and here. The dm cube will cancel out here and here. So basically the answer would be numerically the same. In other words, the answer would be 164 milligram per milliliters, all right? So that basically is how the C part is answered. Okay, any questions concerning the D part? Any questions? Okay, so let me go back to the PowerPoint. And the next thing we're going to talk about is dilutions. And this is another exercise that is routinely done in labs all over. Very often, an experiment might call for a particular solution of a particular concentration. And what you have at hand in your lab, in your storage, would be a solution of a greater concentration. So therefore, what you need to do is to dilute that solution to get the solution of the concentration that you want. But you need to be careful, because you need to know how much solvent you need to add to it in order to dilute it correctly. The key thing you need to remember when it comes to dilution is that when you add a solvent, it does not change the amount of solute, right? The amount of solute remains the same, but the volume is changed, all right? So let me, okay, so this is what is demonstrated here in these pictures, right? So you have your more concentrated solution. I think this is copper 2 sulfate. And what this person did was used a pipette. I don't know if you're familiar with that piece of glassware, but it measures accurately a particular volume. Yep, they come in different sizes. You have the 5 mil, you have the 10 mil, 15 and upward, right? So this here is a 50 mil pipette. So you measure 50 mils of this solution, and this label is so small I cannot see what the concentration is. So sorry about that. But anyway, so this person measured 50 mils of the solution and transfers it into this, which is called a volumetric flask, which is a piece of glassware, which again measures accurately a particular volume. So this person allowed the liquid to drain into the volumetric flask, and then after that adds water to the solution up to the required mark, and therefore ends up with the more dilute solution. All right, so that's basically a step-by-step process that is followed when it comes to solution dilution. Okay, key thing you need to remember again is that the amount of particles present as far as the solutes are concerned are not changing. So the amount of solute doesn't change, but the solution concentration decreases, all right? Okay, that's it for this chapter, which is chapter 3. And unless there are no questions, we're going to move on to chapter 4. So let me go here. And chapter 4 deals exclusively with aqueous solutions and chemical reactions in aqueous solutions, all right? So a couple of things you may have learned in this chapter from before, but there are a couple of things I'm going to introduce to you which you would not have learned in your introductory chemistry courses. So the first thing we're going to discuss here are the electrical properties of solutions, aqueous solutions, all right? In order for us to understand that, we need to reacquaint ourselves with the notion of charges. You have positive and negative charges and how they behave towards each other. So what this diagram here is demonstrating is the nature of charges. If you have two particles that are opposite in charge, as shown here, they will attract each other if they're close enough. If you have two particles which are of the same charge, as shown here and here, they will repel each other. Now, if you have two particles with no charges, there will be no repulsive or attractive forces between them, all right? So that's basically with how the charges behave. And if you are familiar with simple bar magnets, which I'm quite sure we all are, and we play with them, you know that if you bring two like poles close to each other, they will repel. But if you bring two unlike poles close to each other, they will attract each other, all right? Okay, so with that out of the way, let's talk about the nature of ions in an aqueous solution. So if you take any ionic compound and dissolve it in water, right? What will happen is that the ions which were rigidly in a crystal structure will start dispersing itself to form a solution. So therefore, in the solution, you're going to have free floating ions moving around the solution. The same is true if you were to melt an ionic compound, right? If you melt an ionic compound, if you heat it to a high enough temperature, then you're going to break the ionic bonds and the ions will be free to move around in the molten form of that compound, right? So if we're talking about the molten form or the aqueous solution of ionic compounds, what you'll find is that one property that they display is that they're very good conductors of electricity. In the solid state, ionic compounds cannot conduct electricity, but if you melt them or if you dissolve them in water, they will conduct electricity. And the reason why they conduct electricity is because of the free-flowing ions that are present in the aqueous solution or in the molten state. And that is demonstrated by this diagram right here, right? Remember, ions, when they dissociate, they form cations and anions. So we have the free-flowing anions and cations here. Now, let me explain this setup. We have an electricity source connected to two metal pieces here. One is known as the anode, which is positively charged. The other one is known as the cathode, which is negatively charged. So if you connect these two electrodes to the electricity source and dip them into the solution, you're going to have a circuit. You're going to have a flow of electrons in the external circuit here. and you're going to have a flow of ions within the aqueous solution. So an electric current will be basically flowing through this entire system, all right? And that's basically the behavior of ionic compounds. If they're in a molten state or if they're in a solution, aqueous solution, they will allow for an electric current to pass through it, all right? There's some terms that you need to be aware of. I mentioned the anode and the cathode here earlier. But there's some other terms in relation to the solutes themselves or the solutions themselves. So there are three types of solutions when it comes to their ability to conduct electricity. You have what are known as non-electrolyte solutions. These are solutions that do not conduct electricity. And this is found in solutions containing molecules, not ionic compounds, but molecules. So for example, in a solution such as methanol or sugar solution, those are two examples of aqueous solutions that will not conduct electricity. And you can see that in this picture right here. So this is a setup for the experiment dealing with trying to conduct an electric current through a solution of methanol. Methanol is a molecule. It does not exist as an ion in an aqueous solution. So when you complete the circuit, no light is shown in the bulb, right? The bulb will not light up, and therefore that indicates that no current is passing through. So therefore, this solution is known as a non-electrolyte solution, all right? Then we have another category known as strong electrolytes. And these are solutions where you have the complete allowance of electric current to pass right through it, all right? So a good example of this would be sodium chloride. Sodium chloride, when added to water, forms sodium and chloride ions. And this is a complete dissociation, and therefore you'll have a lot of ions floating around the solution, and that would allow for an electric current to pass through, as demonstrated by this picture. As you can see, this bulb lights up, so therefore we know that this is a solution of a strong electrolyte. Now over here, we have a solution of acetic acid. The bulb will light up, but not as brightly as in the case of sodium chloride. And the reason why that is so is because acetic acid is said to be a weak electrolyte. In other words, it does not allow for the conductance of electric current to pass through very greatly. It only allows the electric current to pass through, but it will be a weak current that will pass through that solution. And the reason for that is because in the case of a weak electrolyte, it does not contain mostly ions. It contains mostly molecules. Now there's a small fraction of the molecules that will be converted to ions, and therefore that's a reason why the bulb lights up, but it does not light up as brightly as in the case of the sodium chloride, all right? So that's the difference between the strong electrolyte and the weak electrolyte. Okay, some other things I need to introduce to you here. The use of square brackets like this. They're used to represent the molar concentrations in units of molarity, right? So if you see something, let me get out of this briefly. Let me clean this up. Okay. So if you see something like this, this means the concentration, I should say the molar concentration of HCl. So that's how you interpret that representation, all right? That's what the square brackets represent. Okay. So if you look at sodium chloride undergoing complete dissociation, right? Based on the equation you see here, 1 mole of sodium chloride will dissociate to form 1 mole of Na plus and 1 mole of Cl minus, right? So therefore, if the concentration of sodium chloride originally is 0.010 m, that means that the concentration of sodium and the concentration of chloride will be each the same because of the 1:1:1 ratio based on the equation for the dissociation. Here's another example. If the original solution of this sodium sulfate solution is 0.010 m, that means that based on the equation showing the dissociation, the concentration of the sodium will be twice the original concentration of the sodium sulfate. So the concentration of the sodium ions would be 0.020 m, and the concentration of the sulfate ion would be 0.010 all right? So that's how you can determine the concentrations of the ions. It's basically based on the stoichiometry of the dissociation of these ionic compounds when they are dissolved in water. Okay, if you understand the terms strong and weak electrolytes, then you should be able to understand the terms strong and weak acids as well. Strong acids are acids that undergo complete ionization in water and therefore are good conductors of electricity. Weak acids, on the other hand, undergo partial dissociation. So therefore there'll be mostly molecules, there'll be a few ions, and therefore weak acid solutions will conduct electricity very weakly, all right? And in terms of showing the dissociation of a weak acid, we use a double arrow to indicate that the dissociation is not complete. So this is what we're talking about here, right? In the case of acetic acid, we use this representation to indicate that the reaction is going back and forth. So therefore, it's not just going in one direction to go to completion. And what that means basically is that you're going to have a relatively high concentration of the acetic acid molecule and a low concentration of the ions. Okay. Give me a minute. I need to step out just for a short minute and I'll be right back. Okay, sorry about that. Any questions so far?
Yeah. With the strong acids, the way they dissociate in a solution, is that why sulfuric acid is used in car batteries?
Well, that's one reason. And to fully answer that question, it would take a long time, but sulfuric acid is needed in order to make the battery work. And it has to do with electropotentials and so on. It's a long story, which you will get a chance to explore in Chem 2. Because in Chem 2, there's a whole chapter dealing with electrochemistry, and the topic of batteries do come up in that discussion. And then you'll understand, why sulfuric acid is needed. But you're right about it being able to dissociate strongly. That's one thing that is necessary. You could not use something like acetic acid in car batteries because acetic acid undergoes incomplete dissociation.
Cool.
But there's more to it than that, as I said before. So you have to wait until you do Chem 2 electrochemistry before you can appreciate, the reason why sulfuric acid is needed. Okay. Any questions? Any other questions? Okay. So how do we recognize strong and weak acids, right? Well, the molecular formulas for strong acids are typically written with the hydrogen at the beginning, like HCl and H2SO4, right? So if you see that sort of representation, more than likely the acid is a strong acid. On the other hand, weak acids tend to have the hydrogens in their formulas placed at the end, such as in the case of acetic acid. But that's not always true. There are some textbooks I've seen where in the formula for acetic acid, they put the hydrogen at the front. So that would not be a good guide for you to use to determine which acid is strong, which acid is weak. So this is what you need to do. You need to memorize these 6 acids as strong acids: hydrochloric, hydrobromic, hydroiodic, nitric, sulfuric, and perchloric acid, right? You need to memorize these as strong acids, all right? Now, let me just say something about sulfuric, because sulfuric is kind of different from the others in this list. Let me go back to my writing pad here. You'll notice that the formula for sulfuric acid has 2 hydrogens, right? It turns out that when you add sulfuric acid to water, the first dissociation is strong, HSO4 minus, right? Goes in one direction, you don't have the reaction reversing, right? On the other hand, the second dissociation is weak. All right, so that's how sulfuric acid behaves. The first dissociation is strong, so you have a lot of ions being produced as a result of the first dissociation, but the second dissociation is weak, so the concentration of the sulfate ion present would be relatively low. All right, so that's just something I thought I should point out to you when it comes to sulfuric acid compared to the others. The others don't have what doesn't have more than 1 hydrogen, so therefore they all completely dissociate in the case of the others. But in the case of sulfuric acid, there are 2 dissociations that you can have. The first one is strong, the second one is weak. You had a question?
Does that have I mean, I'm still on the car batteries, but does that have an effect on why you would use that for electrochemical purposes?
Not sure, to be perfectly honest. To be perfectly honest, I'm not sure if the 2-step dissociation has any effect. I'm quite sure it does, but I couldn't say, to be perfectly honest.
Cool. Thanks. Right? Thanks anyway.
Yeah, no problem. Okay. So remember, you need to memorize these 6 strong acids. Pretty much any other acid you're given will be weak unless you're told otherwise, all right? Okay, then we have the bases. Bases are strong and weak. You can have those 2 types. And again, the same principle applies. Strong bases undergo complete dissociation in water. They're usually ionic hydroxides, like sodium hydroxide, potassium hydroxide, and so on. Weak bases, of course, undergo partial, dissociation to form hydroxide ions. The most common weak base one can point to as an example is ammonia. Let me show you how ammonia, in fact, let me see. Do I have that equation? No, I don't. Okay, so let me go here again. In the case of ammonia, the way it acts as a base is that it reacts with water according to this equation. NH4 plus OH minus, right? And because the reaction produces hydroxide ions, then ammonia is said to be a base, all right? So that's basically ammonia basic character. And this is true not only of ammonia, but there are other nitrogen-based compounds, especially organic compounds, that behave similarly, all right? Okay, so that's as far as strong and weak bases are concerned. Again, you need to memorize some strong bases here. Now, this is an easier list to remember because these are all hydroxides of group 1A and group 2A, right? So lithium all the way down to cesium hydroxide in group 1A, and then magnesium all the way down to barium hydroxide as far as the group 2A hydroxides are concerned. So make sure that you commit these bases to memory as being strong, and pretty much any other base that you're going to encounter will be weak unless you're told otherwise, all right? Okay, let's see here. Okay, so now we're going to talk about a neutralization reaction in more detail. I think we talked about it earlier. So just to refresh our memory, the neutralization reaction is a reaction between an acid and a base to form a salt and water, right? Now, the reason why neutralization is the term that was used for this reaction is because supposedly the products will be neutral. You start off with something acidic reacting with something basic, and you should end up with products that are neutral. Let me just say that this is not always true. right? There are some instances where the salt that is produced can be acidic or basic, and it depends on the nature of the acid and base that's involved. Of course, I won't get into that right now because that would be a topic that you're going to encounter in general chemistry too. In this case, however, in the case of the reaction between potassium hydroxide and hydrochloric acid to form potassium chloride, the potassium chloride is actually neutral. Of course, water also would be neutral as well, all right? So what we're going to look at is actually what happens in these reactions, because the equation just tells us the overall description of what is happening in the reaction. So we're going to figure out what is called the net ionic equation for this reaction. And now, in order for us to figure out the net ionic equation, we have to figure out basically what ions involved in the reaction are spectator ions, which means that they basically sit around and watch what's happening. And then whatever is left would be the participating ions, which would be actually involved in the reaction, all right? So this equation here is the overall equation for the reaction. In most textbooks, they call this the molecular equation, even though the term molecular is a bit of a misnomer because not all of these are molecules. Potassium chloride is definitely not a molecule, and the same is true for potassium hydroxide, all right? So the next question we have to ask ourselves is, how will these dissociate if they will dissociate? How will they split up, all right? Now we know that hydrochloric acid is a strong acid. So hydrochloric acid will split up to form hydrogen ions and chloride ions. Potassium hydroxide is a strong base. So we know that that will split up to form potassium ions and hydroxide ions. The water is a molecule. It's not ionic. So therefore, it will not dissociate. So therefore, the H2O will remain undissociated as shown here. And then we get to the potassium chloride. Potassium chloride is an ionic compound. Any ionic compound that is dissolved in water will dissociate. And we know that this is soluble in water because we have AQ right here. So therefore, KCl will split up to form K plus and Cl minus. Okay, so this second equation here, we call it the ionic equation. What we're trying to get to is the net ionic equation. And how do we do that? We identify the spectator ions. So the spectator ions are those species that remain unchanged on both sides of the equation. So if you inspect this equation carefully, you'll see that the chloride ions are on both sides. So therefore, we can cancel them out. And the potassium ions will remain unchanged on both sides. So we can cancel those out as well. And therefore, we simply just write down what is left. And what we're left with is H plus reacting with OH minus to form H2O liquid. And that would be the net ionic equation, all right? So that's basically how we get from the original molecular equation to the net ionic equation. Okay, any questions about this? Any questions about this particular example? Any questions? Okay, so let me spend a few minutes talking about titration. Titration is a technique that is used in chemistry where we use one solution of a particular concentration to determine the concentration or some other information of another solution based on the reaction between the reactants in both solutions, right? And there are different types of titrations. We have acid-base titration, redox titration, precipitation titration. There are different titration techniques, all right? So since we were just talking about acid-base titration, let me refer to that with respect to this process. So one reactant is placed in a long cylindrical burette apparatus. I don't know if you know what a burette looks like. Let me see if I have a diagram here. No, I don't, unfortunately. But a burette is a long cylindrical apparatus, glassware, and you basically pour your liquid into it, and you can deliver specific volumes of that liquid from the burette. And the burette has a tip at the end of it, under which you're going to place a flask, which has the other reactant and a few drops of an indicator, which indicates when you add the right amount of reactant from the burette to the flask. So as stated here, the reactant to the burette, which is called the titrant, is then slowly added to the reactant in the flask until the indicator changes color. And that's basically where you stop adding. And then based on the volumes involved, you can do your calculations to determine the concentration of one reactant based on the concentration of the other. And it's really regrettable that you guys don't get a chance to do this in practice, because it's a very good experiment, a very good analytical experiment for determining the concentration. And it's very, well, of course I'm biased because of chemistry, but it's a fun activity to do when you add, your, let's say, base to your acid until the indicator changes from color to pink, and then you stop adding and then you do your calculations. It's a very nice exercise, which hopefully you'll get to do in the future. Okay. And there are YouTube videos, by the way, which describes it. So you can go on YouTube and just type in acid-base titration, and you'll see a whole lot of videos posted about how to do the experiment carefully and so on. Okay, here are some acid-base reactions which involves the formation of gases, all right? Now, if you take, for example, any compound that contains bicarbonate ions or carbonate ions, and you add acid to them, then you get the immediate formation of bubbles, which is due to the carbon dioxide produced as seen in these two equations here, all right? And you can actually do this experiment at home, right? If you have baking soda contains the bicarbonate ion, and you add to it either lemon juice or drops of vinegar to it, then you'll see bubbles being formed. That is the carbon dioxide that is formed from the reaction. Another reaction that produces gases, acid-base reaction that produce gases, is when you add acid to either the hydrogen sulfide ion or the sulfide ion, right? So compounds containing these ions, when you add acid to them, you're going to have the formation of sulfur dioxide gas. Now, this particular reaction, I would not recommend that you do at home, because sulfur dioxide is a pungent gas. If you're in a room filled with that gas, you start choking, unable to breathe, and all of that. All right, so I would not recommend that you do that reaction at home. And then the final reaction that we're going to talk about here, where gas is formed as a result of an acid-base reaction, is the reaction between an acid and any compound that contains the hydrogen sulfide ion and the sulfide ion. Now, in these cases, you end up with the formation of hydrogen sulfide. And again, I would not recommend that you do this reaction at home, because for one, hydrogen sulfide has a very awful smell like rotten eggs, all right? And for two, it is very toxic, right? If you inhale enough of this, you will literally die, all right? So this is something that I would not recommend that you do at home as well, all right? So these are just examples of reactions, which are acid-base reactions, where gases are formed. Okay, should I get into, I think I'm gonna stop here because this is a rather involved topic, precipitation reactions, all right? So yes, I'm gonna stop here. The next class, which will be next week, Tuesday, we'll be discussing precipitation reactions. Okay, so if there are no questions, that's pretty much it for today. Let me, if anybody came in late. Is Arias here? Nope. Barber?
I'm here.
Oh, there you are. Chang? Not here. Chavis? Not here. DeGraff? Not here. Franklin? Not here. Han? Not here. Panic? Not here. Haron is here. Jurgensen? Not here.
I'm here.
Oh, you're here? Where? Oh,
Yes.
my bad.
You're good.
Rouse? Santiago? Smith? Okay.
I'm here.
Oh, Smith is here. Cool. All right. So that's basically it. Unless there are any questions you guys have. Any questions? No questions? Okay, so that's it. I think I'll be posting another quiz. If not this evening, definitely, definitely by tomorrow. What, you had a question, Mr. Runner?
Yes, I'm glad I remembered this. It's about one of the questions on quiz 2.
Okay.
Concerning significant figures. If
all right, hold on. Let me see if I can bring it up. Let me go to here. No, not there. Let me go to there. And then let me go to files. Let me close this out. Files. And then quizzes. And quiz number 2. Let me download that. And let me share screen, right? Share screen. Okay, can you see my screen?
Oh, yeah.
All right.
Yeah.
So you said question number 2. Oh, okay, this one. 2B, okay.
Yes. The 8.92 minus 8.9. You so when you're adding and subtracting, you figure your decimal points as the smallest number of decimal points in the entire
exactly
in the equation. And that would, so I would get an answer of 0.0.
Exactly. And that's why I designed that particular question that way.
Exactly. So that would make the entire that would make the entire answer 0.
We made the entire answer 0.0. It would still be 0.0.
Yeah.
Right.
Yeah, I suppose you're right, because it would be the smallest number of sig figs in the entire thing. Okay.
Exactly.
Cool.
Exactly. Yeah, that was one of my trick questions.
Thank you. Well, I'm glad I asked.
Yep.
Them.
Okay.
Well,
any other questions? Any other questions about the quiz or anything else? Okay, so if there are no other questions, that's pretty much it for me today. So enjoy your weekend. And oh, by the way, Monday's a holiday, right? Enjoy your holiday. So take care.
That is.
Yeah, I think that's Labor Day, if I'm not mistaken.
Oh, okay.
Yeah. All right. So I'll see you next Tuesday.
Groovy. Take care. Enjoy
Yeah,
your
take care.
holiday too.
Yeah, thanks.